Welcome back to the deep dive. Today we're going to start with a scenario that, well, if we were in any other industry, it would get you fired immediately.
Okay, I'm intrigued.
I want you to imagine you're an architect. You've been hired to build this massive, beautiful library. You design it, you hire the crew, you pour the concrete, frame the walls.
A whole 9 yards.
Exactly. You put the roof on.
Yeah.
And then right before you hand over the keys, you look at the client and you say, okay, that was a fantastic practice run. Let's bulldoze it and build the real one now.
Yeah, that's professional suicide in civil engineering, in construction, manufacturing. That is absolute insanity. It's a financial disaster.
Right. But today, we're diving into the materials for CS326, specifically for Class 6. It's Tuesday, February 3rd, 2026, by the way. And the central idea we're wrestling with claims that in software engineering, that specific kind of insanity is actually the only path to sanity.
It is a bold claim, but when you really dig into the sources we have today, it starts to look less like insanity and more like necessary discipline.
Right. We are covering a lot of ground. We've got reading notes from Fred Brooks's absolute classic, The Mythical Man Month, chapters 11 and 13.
Mm-hmm.
We have the slide deck from the lecture, which has some very specific instructions in a parable that feels a little too real.
Oh, I know the one.
And we have the course syllabus in the background, just to give us context on tools like BitBuddy and Git.
And really, the mission today is to bridge that gap between, 1970s engineering philosophy, which is what Brooks is, and the reality of a student sitting in a lab in 2026.
We need to figure out why building something just to throw it away is maybe the secret to reliability.
Exact.
So let's unpack this throwing one away idea first. It comes from chapter 11 of the Mythical Man Month. Brooks uses an analogy here that I think is just crucial because it explains why software is so different from building a house. He talks about the chemical engineer's pilot plant.
This is such a vital distinction. In chemical engineering, let's say you're inventing a new process. You're in the lab, or, mixing chemicals in a little glass jar. You figure out the reaction. It works perfectly.
Okay.
You absolutely cannot take that recipe, multiply the quantities by 10,000, and just dump it into a massive factory vat.
Wait, why not? I mean, if the ratio is the same, shouldn't it work?
You'd think so, but the physics change at scale. The heat dissipation is totally different in a giant tank than in a test tube. The pressure dynamics change. If you scale up immediately from the lab to production, the factory, well, it probably explodes. So they build a pilot plant. It's an intermediate step, a mini factory.
And the purpose of this pilot plant isn't to actually produce the chemical for the customer.
No, not at all. The purpose of the pilot plant is to figure out how to build the real factory.
So it's a learning tool.
It's just a learning tool. And here's the kicker. Once they learn the lessons from it, they usually just dismantle the pilot plant. They don't try to retrofit it into the final product.
And Brooks is saying software is identical to that. The reading notes really emphasize that the first version of any new complex system is almost inevitably slow, big, and awkward.
Slow, big, and awkward. Those are his exact words. And honestly, just think about the first draft of code you write for any hard assignment. It's usually a mess, right?
Of course.
You're discovering the problem as you are solving it. You don't realize your data structure is inefficient until you actually try to run it with real data.
So you build this first version, it runs, it technically does the job, but it's a mess under the hood. Now here's the trap. And I think this is where the students in CS326 and frankly, most startups get into so much trouble.
Right.
You have a deadline, you have a budget, you have this slow, big, awkward thing that basically works. The temptation to just polish it up and ship it must be overwhelming.
That is the siren song of failure. Brooks argues that if you deliver that throwaway version to the customer, if you try to pass off the pilot plant as the factory, you're setting yourself up for disaster.
The notes are so dramatic about this. They say delivering it causes agony for the user, distraction for the builder, and a ruined reputation for the product.
Agony for the user.
Okay.
That's strong language.
But I can see it. If I'm using software that crashes every time I click a certain button, yeah, that is agony.
Exactly. And for the builder, it's a total distraction because instead of working on the next great feature, you're spending all of your time just patching a system with a broken foundation. You're bailing water out of a boat that has a hole in the hull.
So the argument is, you are going to throw the first one away eventually.
The system will force you to. The only choice you have is whether you plan for it and build that time into your schedule, or if you ship the garbage, watch it fail, and then have to rebuild it while the customer is screaming at you.
So the mantra is, plan to throw one away.
Hmm.
It's such a paradox. To be fast, you have to be willing to waste work.
Yeah.
But Brooks points out something really interesting about why this is so hard for people to accept, specifically with software. He calls it the illusion of tractability.
This is a fascinating psychological point. If you're building a skyscraper and the client says, you know what, I want the elevator shaft on the other side of the building, you just say no, because everyone can see the concrete. Everyone sees the steel beams. It is physically obvious that changing the foundation is unbelievably expensive.
But software is just text on a screen. It looks weightless.
Exactly. It looks like you can just highlight a block of code, hit backspace, and type something new. This creates an illusion for managers and customers, and dangerously for developers themselves, that requirements can change without any cost. Oh, just add this feature, just change that interface.
And the reality is, the user never knows what they want until they see what they don't want.
Precisely. The notes mention that user needs change as they see the product being built. You show them the pilot plant and they go, oh, I didn't realize that button would be so hard to reach. They can't articulate that until the prototype exists.
So if you plan to throw that prototype away, you're fine. If you plan to keep it, you're in deep trouble.
Which leads right into this concept that sounds almost like a physics term: maintenance entropy.
It's borrowed from physics, right? Entropy is the tendency of a system to move toward disorder.
It is. Now, we usually think of maintenance like maintaining a car, as replacing parts that wear out. You know, the tires go bald, the brake pads grind down. But software doesn't wear out.
The bits don't get tired. The code doesn't rust.
Exactly. So what is software maintenance then? The notes clarify this beautifully. It isn't repairing wear and tear, it's repairing design defects.
Or adding new features.
Or adding new functionality that forces the system to do something it wasn't originally designed for. And here's where the entropy comes in. The notes point out a specific, terrifying risk. Fixing a bug has a substantial probability, some studies say 20 to 50% of introducing a new bug.
That's the 2 steps forward, 1 step back nightmare.
Or sometimes it's 1 step forward, 2 steps back. Every time you touch the code to fix something, you are disrupting the structure. You're adding complexity. You're increasing the disorder.
And eventually the system becomes so high entropy, so disorganized from all these patches and band-aids that it's unfixable. You touch one line of code here and a feature breaks 3 modules away.
The notes mention a statistic that maintenance cost is estimated at around 40% of the building cost. And frankly, in the modern world where software runs forever, it's probably way, way higher than that.
Oh, absolutely. Which means if you build on a bad foundation, you are locking yourself into years of expensive misery. Brooks also touches on how this impacts the people, not just the code. There's this mention of the dual ladder of advancement.
This is a huge issue in tech. In a lot of traditional companies, the only way to get a raise or promotion is to become a manager. So you have a brilliant coder, the best on the team. To reward them, what do? You make them a manager.
And suddenly they aren't coding anymore. They're just sitting in meetings.
And they might hate it. Or worse, they might be terrible at it. Managing people is a completely different skill than managing memory pointers. So the company loses a great engineer and gets a mediocre manager. It's a lose-lose.
So the dual ladder is the solution to that.
Right. You need a path where technical people can advance in prestige, title, and pay equivalent to management without having to stop being technical. But, and the notes are careful here, this requires cross-training.
The technical guru needs to understand the business, and the manager needs to understand the tech.
To reduce that overhead of communication.
Okay, let's pivot to Chapter 13. We've talked about the life cycle, the pilot plant. Now let's zoom into the actual design process. The chapter is titled The Whole and the Parts, and the core concept is conceptual integrity.
This is moving from the macro to the micro. The core problem Brooks identifies here is just so insidious. He says the most difficult to find bugs usually don't come from bad syntax.
Right, not from a missing semicolon.
No, those are easy. The compiler screams at you for those.
Yeah.
The nasty bugs come from mismatched assumptions between the authors of different components.
Can you give me an example?
Okay, sure. Imagine you and I are writing a system. I'm writing the part that saves a user's birthday. You're writing the part that calculates their age. I assume the date format is day, month, year, because I'm European. You assume it's month, day, year because you're American.
And the code compiles perfectly. The computer does exactly what we told it to do.
But the system is broken. If I enter the 3rd of February, 3/2, you might read it as March 2nd. The logic holds, but the integrity is gone.
So Brooks argues for top-down design. Architecture first, then implementation.
And remarkably, the notes suggest that an outside group has to test the specifications.
That stood out to me. Why an outside group? Why can't the team just test their own specs?
Because we have blind spots. If I wrote the spec, I know what I meant. So when I read it back, my brain subconsciously fills in the gaps. I don't see the ambiguity because I already have the answer in my head.
But an outsider doesn't have that context.
Right. They look at the spec and say, hey, what happens if the user enters a negative number? And you go, oh, I didn't think of that. You catch the bug before a single line of code is ever written.
That's incredibly high leverage. Fixing a bug on paper costs $10.
Wow.
Fixing it in production costs $10,000.
Yep.
Now, speaking of testing, there's a term in the notes, scaffolding. If I'm a student, I might think, I don't have time to build scaffolding. I barely have time to build the assignment.
And that is exactly why students struggle. In construction, scaffolding is the temporary structure you stand on to build the wall. You take it down when you're done. In software, scaffolding refers to dummy components or mock objects.
So writing code that you know for a fact you aren't going to ship.
Correct. Let's say you're building the user interface, but the back-end team hasn't finished the database yet. You can't just sit on your hands. So you build a mock database, a little piece of code that just returns fake data. It lets you test your interface to make sure it handles data correctly.
It decouples your progress from the other team's progress. Okay, there was one vivid detail in the notes I have to bring up. The purple wire technique. It sounds like a spy novel or something.
It does. This is old school. Back in the days of mainframes, the circuit boards were massive and expensive to manufacture. If you found a mistake in the wiring after the board was printed, you couldn't just hit backspace.
You'd have to throw away a $10,000 board.
So what they did was technicians would solder a literal purple wire across the back of the board to bypass the mistake. It was a visual standard. If you opened up the machine and saw a purple wire, you knew instantly. That's a patch. That's a quick fix. It is not part of the original design.
It's a warning label.
Exactly. And Brooks applies this to software. We need a purple wire for code. We need a way to identify code that's a quick patch, a hot fix, something that breaks the architectural purity.
In modern terms, this would be handled by your issue tracker or Git, right? Like a tag.
Yes. You tag the release as a hotfix. You don't hide it. You need to know which parts of your system are solid architecture and which parts are purple wires just holding it all together.
Okay, let's bring this down to earth. We've covered the high theory, Brooks, the pilot plant, the triple wire, but we also have a slide deck from the actual class, CS326. And there's a slide here titled, As We Generate Ideas, that feels like a direct attack on every group project I've ever been a part of.
The As We Generate Ideas slide. It's the parable of everybody, somebody, anybody, and nobody.
It's a classic. There was an important job to be done, and everybody was sure that somebody would do it. Anybody could have done it, but nobody did it.
It sounds like a riddle, but it is the reality of undefined responsibility. The context here is key. The class has been generating ideas for standards for their development shop, but the slide is a warning. If you just have a list of good ideas, but no one is assigned to implement them, nobody will do it.
And the slides get very specific about who somebody needs to be. It calls out the discussion leaders.
Right. This is a direct instruction for the discussion leaders. They are responsible for updating the wiki. They have to document the decisions in the open items. If the discussion leader doesn't do it, the system fails. Accountability has to be assigned to a specific individual.
Speaking of accountability, the slides lay out some very specific new standards for Git. This is where we move from nobody doing it to you doing it.
Right. No more ambiguity. The instruction is explicit. They're moving to a system where all reading notes have to be submitted via Git.
And look at the details here. It has to be in the reading notes directory inside the CS326 individual lab work project. And the naming convention is totally non-negotiable. YYYYMM-DD.pdf.
So for today, that file better be named 2026-0203.pdf.
It seems so trivial, though. Why do we care so much about the file name? Is the professor just being difficult?
No, this ties right back to conceptual integrity. If you have 30 students and everyone names their file differently, mynotes.pdf, feb3notes.pdf, Dave's notes automation becomes impossible.
You can't write a script to collect them.
The system breaks. Following the naming convention is a test. Can you follow a simple spec? Can you integrate your work into the whole without breaking it?
It's a test of discipline. And speaking of testing yourself, there is a mention in the slides of a web development project, Music Depth. This looks like a major step up from the labs.
This is a real-world client situation. Professor Prasad needs a web-based graphical interface for music analysis using SVG's scalable vector graphics.
The slide notes, it isn't required, but it's a major resume builder.
This is the perfect pilot plant laboratory. You're working for a real person, not just a grader. You are going to build something, show it to Professor Prasad, and I guarantee you he's going to say, that's not quite what I meant.
And you'll have to iterate.
You will have to throw parts of it away. If you go into that project thinking your first draft is the final product, you will fail. If you treat it as a discovery process, as a pilot plant, you'll succeed.
Just a quick check on the immediate logistics for the listeners who are in the class. Lab 2 is due Thursday, February 5th. And again, don't forget that nobody parable discussion leaders, update that wiki.
If you think someone else is doing it, I promise you they aren't.
Before we wrap up, I want to touch on the syllabus just quickly. We mentioned the modern toolkit. The syllabus talks about LLM integration BitBuddy.
And specifically, the requirement for payload IDs.
How does this connect back to Brooks? I mean, Brooks was writing in the 70s. He didn't have ChatGPT.
He didn't, but he talked about integrity. In the syllabus, there is a strict requirement for citation. If you use AI to generate code, you must cite the payload ID. You have to know where your code comes from.
This feels like the modern version of the purple wire.
It is exactly that. If you use an AI to write a function, that's a black box. You didn't write it. You might not fully understand it. You are basically soldering a purple wire into your code base.
You have to tag it.
You have to track it. Because if that code breaks 6 months from now, you need to know, oh, I didn't write this logic the AI did. I need to review it from scratch.
And if you don't cite it, you're hiding the purple wire. You're pretending the patch is part of the original design.
And that is so dangerous. It destroys the conceptual integrity of the whole system because you have this alien DNA in your code that you're not accounting for.
The syllabus also sets up specific team roles. Chief Understanding Leader, Chief Equity Leader.
Again, this addresses the overhead of communication we talked about earlier. By assigning someone to specifically make sure everyone understands the plan, you're designing the team just like you design the software. You're not leaving communication to chance.
It's all connected. The code, the team, the documentation, it's all one system.
It is.
So let's recap what we've covered today. We started with this wild idea that you should plan to throw your first version away because it's a pilot plant, a learning tool, not a product.
We discussed maintenance entropy, the idea that software structure just degrades over time as you patch it, eventually leading to a system that costs 30% of your budget just to keep alive.
We looked at conceptual integrity and the purple wire, the need for rigorous testing, scaffolding, and transparently tracking your hacks and patches.
And we brought it right down to the immediate reality for the students. The responsibility to update the wiki so nobody isn't left holding the bag, and the discipline to name your Git files correctly.
It seems like the big takeaway for you, the listener, today is that while coding feels like this creative, fluid art form just typing text on a screen, the thing that keeps it from becoming a disaster is structure.
Absolutely. Creativity needs constraints. Scaffolding, version control, naming conventions, these aren't just bureaucratic red tape. They are the structural steel. They're what keep the building from falling down when you decide to add a new floor.
So here is the question we want to leave you with today. It comes back to Chapter 11. If you know for a fact that your first attempt at a project, whether it's Lab 2 or that music dep project, is destined to be thrown away, does that liberate you? Does it make you feel free to experiment and take risks, knowing it's just a draft? Or does it terrify you because it feels like you're wasting time and budget?
And more importantly, how should that answer change the way you type your very first line of code today? If you know it's a throwaway, maybe you stop trying to make it perfect and you start trying to make it instructive.
Something to chew on. Thanks for listening to The Deep Dive. We'll see you in the next one.